Hello, welcome back. In the previous lesson, we introduced the concept of electric potential, a landscape created by electric charges whose slope at each point is proportional to the electric field at that point. The electric field is the gradient of the potential, the negative gradient of the potential. The potential and the electric field do not depend on the test charges, and the force that the test charge feels is proportional to the electric field. So, in the end, we measure the force on a test charge that we put at a specific point for that particular purpose. The steeper the potential at a specific point, the larger the electric field in the opposite direction. We write that E is equal to negative nabla V. We can think of a specific shape for the potential and calculate the electric field at a given point. But if we raise or lower the whole potential landscape by a constant, the slopes remain the same, and the electric field and the force do not change. What we actually care or measure is not the potential, but the potential difference. When you go to the lab and use your multimeter to measure potential, what you actually do is measure the potential difference between two given points. This is also known as the voltage between those 2 points. You put one of the probes in contact with point A and the other probe in contact with point B, and then you obtain the potential difference, the voltage, between points A and B. It is important to have the same reference point for all devices and parts of the circuit, the same origin of potentials. In that case, all instruments should be connected to the same origin, which is the ground or earth. Now, let's go back to this equation. The electric field is the negative gradient of the potential. If we go the other way around, we can write it as the potential difference between points A and B are the negative integral of the electric field along the path that goes between A and B. For example, for a point charge, we have that the electric field is kq over r squared. To know the voltage between A and B, we integrate. We evaluate between A and B. If we integrate between infinity and a distance r, this is the electric potential created by a point charge q. The electric potential at infinity is 0 in this case. May science be with you.